Welcome back, everyone. In this lecture, we're going to discuss LSTM and GRU units. Many of the solutions previously presented for vanishing gradients can also apply to recurrent neural networks, or the recurrent neuron. That is, things like using different activation functions, such as rectified linear units, performing batch normalizations, etc. However, because of the typical length of a time series input, especially if the time series happens to be really long, what could happen is using those different activation functions or some of those other solutions that could actually slow down training time. Now, a possible solution to that would just be to shorten the actual time steps that you're using for prediction. So maybe instead of looking back 24 time steps for the 25th prediction, you just look back 3 time steps to get the next prediction. However, this makes the model worse at predicting longer trends. So we still want to be able to use a long time sequence in order to predict the next item in the sequence or element in the sequence. Now, another issue that recurrent neural networks face in general is that after a while, the network will begin to forget those first inputs, as information is lost at each step going through the recurrent neural network. What we need to do is to have some sort of long-term memory for our networks. So as you can imagine, this is where the LSTM memory cell or neuron comes into play. And LSTM stands for long short-term memory. So we're going to have both long-term and short-term memory going in and out of that cell. And this was created to help address these typical recurrent neural networks issues. So let's go ahead and get an understanding of how an LSTM cell works. But first, let's quickly review what's happening in a normal recurrent neuron. So in a typical recurrent neural network where you don't have any specialized cell types, you're taking in the input at some timestamp, and then along with the output at that timestamp, you're feeding that back in to the next timestamp. So your input at t-1 produces an output at t-1, and you take that output and feed it back into the next time step along with the input then at time t. So essentially now you have 2 inputs, you create a single output, but pass in that same output into the next timestamp and so on. So if we just take a look at what a single recurrent neuron would actually be doing, is essentially it's taking in both the previous output and then the current input, and then producing the next output. And what we'll do in order to label these with equations is, instead of saying output or input, we'll simply refer to these as hidden state and then our current feature x going in. So basically, we have the h of t-1 going in along with x of t, and that produces h of t. And then what is actually happening inside of the neuron? So in a standard recurrent neural network, essentially what we do is we just have a single hyperbolic tangent function. And then what we're doing is we're combining h of t-1 along with x of t, multiplying it by some weight matrix, and then adding a bias to it, and then passing it through the hyperbolic tangent function, and that gives us back out h of t. And then we just repeat that through the next recurrent neuron, or next recurrent layer. So an LSTM will also have this chain-like structure, but the repeating module has a slight difference to it. And instead of just having a single neural network layer, there's actually going to be 4 layers working and interacting in a special way. And the way we end up getting 4 is the fact that not only will we keep track of just a single historical memory with h of t-1, but we're keeping track of both the long-term memory input and the short-term memory input, and then creating a new long-term memory output and a new short-term memory output, along with the current input at time t, and then we produce an output at time t. So don't worry too much about these details right now. What we're going to be doing is walking through the LSTM step by step. But for right now, let's just get comfortable with some of the notation we're going to be using. So essentially, we're going to have 4 main components inside the LSTM. We have a forget gate, an output gate, an update gate, and an input gate. So as you can imagine, and we'll go over this in more detail later on, but the forget gate will decide what to forget from the previous memory units. The input gate will decide what to actually accept into the neuron, and then the update gate will update the memories, and then the output gate will actually output the new long-term memory. So a gate, just to clarify this, optionally lets some information through. And essentially we can just think of this as, mathematically, it's a sigmoid function. It's either going to end up being a squeeze between a 0 or 1, and if it's 0, we don't let that information through, and if it's a 1, we do. Okay, so again, here's our general structure of the LSTM, and we're accepting both long-term memory and short-term memory, and we can kind of think of this as going to be passed in through conveyor belts inside of this neuron. And what ends up happening is it just ends up kind of running down straight the entire chain and has some kind of linear interactions with a few functions inside of the cell. Now, for the purpose of mathematical notation, we're going to relabel some of these, and we're going to label it as such. We're going to say we have on the bottom there an x of t input leading out to your h of t. And notice then we have that short-term memory. So we'll call the short-term memories on the bottom here. So we're going to call that h of t minus 1 and h of t. And then we're also going to not just have that hidden state, but we'll also have c of t minus 1 and c of t, which is going to refer essentially to our long-term memory. Okay, so what are the actual linear interactions and functions going on inside of LSTM? Well, here we can see the entire LSTM cell. So what we're going to do is essentially go through the process step by step. All right, the first step in our LSTM is to decide what information are we going to throw away from the cell state. Essentially, what are we going to forget? So what we end up creating is a forget gate layer, or f of t. And remember, those gates are essentially just passing in things through a sigmoid function, where the closer it is to 0, that means the less weight you're giving it. The closer it is to 1, that means the more weight you're giving it. So in the context of a forget gate layer, the closer it is to 0 essentially means forget about this and get rid of it. The closer it is to 1 on this output means completely remember this. It's probably important that we remember this. So this is what this f of t is doing. And notice that it's essentially a linear combination of h of t minus 1, that previous hidden state, combined with the input at x of t, and then we have our own sets of weights for this forget gate layer, plus a bias, and then we pass it through an activation function, and then we get f of t. Then the next step after this is to decide what new information are we going to store into the cell state. So this has two parts to it. First, we can see here on top, we have a sigmoid layer that we're going to label the input gate layer, which is essentially going to decide what values are we going to update. Next, we have a hyperbolic tangent layer that creates a vector of new candidate values, which will say c of t, but we'll label this with a tilde on top of it to essentially say, hey, these are the new candidate values that will eventually, hopefully, in some sort of weighing, be updating the cell state. So we have that input gate layer, again, deciding which values we're going to update, and that hyperbolic tangent layer, which is creating a vector of those new candidate values. Notice again, they're essentially just linear combinations of x of t with h of t minus 1, and then we have them being multiplied by their own set of weights, and we add a bias to it, and we're passing them through activation functions. Then, it's now time to update the old cell state, which is c of t minus 1. So what we do is, in order to calculate the new cell state, c of t, that we're going to end up outputting, we have c of t is equal to f of t multiplied by c of t minus 1, and then we're going to add I of t times those new candidate values. So essentially what we're doing is we just multiply the old state by f of t, forgetting the things that we decided weren't that important due to the forget gate layer. Then we added I of t times the new candidate values. So essentially, these are the new candidate values for the cell state scaled by how much we decided to update each state value. So then finally, after this, we need to decide, well, what are we actually going to output? So this output will be based on our cell state, but is actually a filtered version. First, what we end up doing is we run a sigmoid layer, so that's that top equation, which decides what parts of the cell state we're going to output. Then, we put that cell state through a hyperbolic tangent function. And what the hyperbolic tangent function does is it pushes all the values to be between -1 and 1. And then we're going to multiply it by the output of that initial sigmoid gate of O of t, so that we only output the parts that we decided to. Now, what I've been describing so far is essentially just your standard normal LSTM. But there are variations of this, which I'll briefly mention. There is the peephole variation, where essentially what we end up doing is we have these peephole connections, if I add it here, as red lines. And this means we let the multiple gate layers, the f of t, I of t, and O of t, look at the cell state. So here, notice that we're essentially adding in c of t minus 1, or c of t, into these three gates. Now, we previously didn't have that. We only had h of t minus 1 and x of t, but In some variations of LSTM, they add in peepholes, which essentially also linearly combines the cell state inside of the LSTM. Another variation off of this is the gated recurrent unit. So what the gated recurrent unit is essentially it's going to combine the forget and input gates into what's known as a single update gate. And it also merges the cell state and hidden state and makes some other changes. So what ends up happening is you have this model that's simpler than a standard LSTM model, and depending on what applications, it's getting kind of popular, but again, the standard has really become LSTM, and then gated recurrent unit is slowly picking up popularity, but by the time you're seeing this, who knows what the current case is, because this is a field that moves very, very fast. So if you want, you can check out the links I have for this lecture to see a kind of in-depth explanation over which variants are the best, how their differences actually matter, and when to use certain units. Okay. Now, fortunately, with our deep learning Python library, we simply just need to call the import for recurrent neural network, or LSTM, instead of needing to code all of this calculations out ourselves. So finally, what we're going to do is let's go ahead and explore how to use LSTMs for deep learning with Python code. I'll see you at the next lecture.